Okay, thank you everyone. So yeah, welcome to our intro to interrupts for the BBC part 2. This time, as I said, you'll be pleased there's no PowerPoints. Last time was all very theoretical, and I think this time we wanted to just cover some practical examples. So I've got a little bit of preamble, but otherwise I've got 4 code samples which I thought we'd just walk through and hopefully just explain a little bit more concretely how interrupts work and how we can actually use them for the things that we talked about, right? The things that we wanted to do. So things like playing music in the background, sorting out our sprites so they don't flicker, timing relative to the raster, and then how this might enable more advanced effects later on. So I thought I'd start just by talking. If you remember last time we talked about we sort of ended on the cliffhanger of system and the user vias. And so these are the 2 chips in the BBC that will generate the interesting interrupts for us that we can use. Now, I'm not going to try and explain in great detail how they work. Again, you can go and have a look in the advanced user guide. But what I'm hoping is that by the time we've gone through this, you can approach that chapter in the advanced user guide with a little bit more confidence, a little bit more understanding. It's a fairly obscure chapter. You know, it's all about the hardware, right? It talks about pins and ports and all sorts of things. It's not immediately obvious when you first start looking at this why, like, how do we use this as a timer, or how do we use this for doing Vsync interrupts. So all I'll say is that we know the two vias, the system via and the user via, and it's important for us to know they have 16 registers by which we interact with them, and they are mapped into the memory map in Sheila. So the system via is mapped in at FE40 to FE4F, and the user via in FE60 to FE6F. And these are the 16 registers. There's a table in the advanced user guide. Again, I'm not going to try and explain what all of these different things mean. We'll actually pull out the individual registers when we go through the examples. But something that it is worth just noting here that the effects that the registers have differ depending on whether you are reading them or writing them. And so you'll see here, particularly when it comes to the timers, when you write to them, sometimes it's a latch, but when you're reading from them, they're a counter. And I'll explain what those mean when we look at the timer example. First of all, though, we are just going to have a little look at 2 of those registers, which are kind of fairly fundamental for us to be able to do anything with these chips. And so I'm going to use the system via as the example, but the exact same thing works for the user via. And the first one we're going to talk about is the interrupt enable register. So this is register 14. And system via, this is located at FE4E. And so our via chip can generate 7 interrupts. These are the names of the interrupts, like CA2, CA1, etc. And these correspond to 7 bits in this register. And if you want to enable one of these interrupts to fire, by which I mean they will, when they're triggered, they will send this signal on the IRQ pin of the CPU, like we talked about last time. Then you need to set bit 7, and if you want to disable the interrupts, then you clear bit 7. And so an example here of disabling all the interrupts on the system via, you would use the value hex 7F here, right? So we're clearing the top bits, and then we are setting all the other bits to say that we want to disable all of these interrupts. And where these interrupts on the system via map, well, we talked about this before in the previous session. So the keyboard is actually mapped here to CA2. The Vsync pulse from the video chip is mapped to CA1, and then other ones like the light pen and ADC, and then our timers. So the timers that we want to use to set up accurate interrupts at different points. And these can have one shot or different types of timer settings. And again, we'll talk about that in the examples. And so to enable the Vsync and timer 1 interrupts on the system via, then you would do it by setting these bits and writing that to the register. And then the other register that's worth talking about is the interrupt flag register. So this is register 13. So on the system via, this is located at FE4D. Because of course, once an interrupt has happened, all it does is send this message to the CPU to say an IRQ has occurred, but we need to figure out which one. And we do that by reading this register. And again, exactly the same thing. These 7 bits here correspond to the same 7 interrupts that we can enable. And these are now set by the the pieces of hardware that are connected to this chip. So a key press will set this bit, and the Vsync pulse will set bit 1, and our timers here, timer 1 and timer 2, will set bits 5 and 6. And again, it's important to note that these, once we've read and we've detected that these interrupts have happened, like we need to clear that flag somehow, right? Otherwise, it will always be set. And we can clear these flags in different ways. And again, probably worth reading the user guide here for more details, but it can be quite subtle. Like some of these side effects of, say, reading one of the timer counter registers will actually clear this flag. And so again, it's probably worth reading in the advanced user guide these exact details. But for instance here, if we want to check whether the Vsync interrupt has actually occurred, we need to read the system via interrupt flag register, so that's FE4D, and then we need to check bit 1, so we check that against the value of 2. And if this comes through, if this bit comes through the AND, then we know that that flag has been set. We know the Vsync has occurred, and we can do something in our interrupt handler. And then similarly here, this clearing the timer 1 interrupt. So this is perhaps not what you would think, but you can do that by just reading this register, this timer 1 low order counter. Right, so moving on to our very first example. So this is running some code in the Vsync interrupt, and we might want to do this in order to, say, play music in the background or just do something else. We know that the Vsync interrupt occurs once a frame, but what is it? And I think this will be a good topic for the future. We were just talking about CRTC, sort of register masterclass perhaps, but for the purposes of this, we can just define Vsync as a pulse that's generated by the video chip that basically tells the TV to start a new frame, right? It tells the TV electron beam in good old CRT terms to return to the top left of the screen and start a new video frame. And that happens, again, for our purposes. We can change this if we want to, but for our purposes, this happens at 50 Hertz for a PAL screen, so every 20 milliseconds. So let's go straight to a code example, and I'll just quickly walk through this and see if there's any questions, and we can have a look at that in the emulator. So all of this, I should say, is on GitHub. It's in my repo here, so this text file and the source for all of these examples is available. But this is going to be a very simple interrupt handler. We're just going to have a little setup here. So we enable the Vsync interrupt by setting that bit and writing it to our interrupt enable register. And then we're registering our IRQ handler, as we talked about in the previous session. And the IRQ handler itself is going to be super simple. We've got our nice well-behaved interrupt handler, so we're storing the accumulator on the stack and restoring it because we want to interact nicely with the OS, and that's how I can demonstrate this in BASIC and just keep things simple. So we're just reading the interrupt flag register, we're checking that bit. If it's not that bit, sure, we'll just pass the handler back onto the MOS. But if it is the Vsync, then we're going to increment a counter that we're just storing in 0 page. And then we're just going to write this to 8 values, which is sort of somewhere up in screen memory, so that we can see whether this is actually having some effect. So I'm going to quickly swap over to JSBeeb. And I've got this set up as our Vsync demo. So you can see here, it's writing into some screen memory. This happens just to the bottom corner of mode 7. But we can go into a different mode. Right? It's just running all the time. It's on that interrupt. And that's just going to carry on forever, doing what it does. And we can read that value out of 0 page. That's just continuing to count up. But this is where you could call a music playback routine, as long as you've got a function that will play a slice of music, a 20 millisecond slice of music, then you could call that here, and you'll be able to play your music on the Vsync interrupt. So the next step from that is to start looking at timers. And so timers are a little bit more involved. So let me just walk through how these work. And we might want to use timers if we want to do something that has to happen on a regular basis, or something that has to be time critical. And the timers in the BIOS are all running at 1 megahertz. So that's 1 million ticks every second. But our timer values are only 16 bits, right? So we can only have 65,000 odd ticks. So we can only actually time, you know, a relatively small delay here. But this is useful for obviously doing high frequency or small timers. And we use these 2 bytes. So there's always going to be a low order and a high order counter. And basically, it's very simple. It counts down, and whenever a timer counter reaches 0, then the corresponding interrupt flag is set. But one important question to ask is, well, when does the timer actually start counting down? And the answer to that is it only actually starts counting when the high order register is written to. And when that happens, at the same time, the low order counter, so this low byte of the counter value, is actually automatically loaded from the latch. And so that's what the latch means. When you put something into a latch, it just sits there. It's not actually used until it's automatically read from the latch into another register. So as an example here, if we wanted to set timer 1 on the system via to count 10,000 ticks, well, the first thing we do is we take the low byte value of our 10,000 and then store that into FE44. And that's actually writing into timer 1 low order latch. Nothing actually takes place, nothing actually happens at that point. And we take the high bytes of 10,000 and we store that in FE45. And so then we're writing into the timer 1 high order counter. And at the same time that happens, the via itself will load the low order counter from the low order latch. And then it will start counting down from 10,000 at that point. Hopefully that makes sense. It's a little bit more complicated than that because the timers actually have different modes. And so you might read about continuous or free run interrupts, free run timers rather, or one-shot timers. And so I just wanted to explain the difference between those two. Basically, all timers will set their corresponding flag whenever they reach 0. But if it's a one-shot timer, then it just stops. Right? It just stops counting at that point. But if it's a continuous or free run timer, then the counter is actually reloaded with a new value. But that value will come from the latch register. So it won't necessarily automatically just load the value that was previously in the counter. It depends whatever is in those latch registers is what gets reloaded. And then a very subtle point that was only relatively recently discovered when, I think it was when Sarah was actually creating the most cycle accurate emulator with BM, that it actually takes 2 milliseconds for the latch value to get loaded into those registers. And so you do need to compensate for that and adjust when you're setting your timer values. And only timer 1 can run in continuous mode. Timer 2 has another mode, I think it's pulse mode. Don't know anything about that. I'm definitely not going to talk about that here, but you can read about all of this again in the advanced user guide. And you set the timer mode using the auxiliary control register. So for example, if you want to set timer 1 on the system via to generate continuous interrupts, then you actually set this bit here, you set bit 6, and that's the timer 1 control. And so you write that into that register, so FE4B. And so say we want, say timer 1 is counting down from some value. If we want that to load 5,000 and count 5,000 ticks on the next time around, then we write that value into the low order latch and the high order latch. So it has no effect on the currently running timer, but when it does reach 0, if it's in this continuous or free run mode, it will automatically then load this value of 5,000 into that timer and carry on. And so I've got another example here. So this time we're going to run a timer at 100 Hertz. So something that should happen twice a frame. And to do that, I'm actually going to use the user via because again, I want to cooperate with the MOS. If you remember from last session, if we hijack timer 1 on the system via, then the MOS uses this in order to do certain things, not least the keyboard. So we're going to use the user via instead, and we can do this in exactly the same way, but we're just using FE6E here to enable the timer 1 interrupt on the user via. And we set up our IRQ handler as per last time, and then we're also here asking the user via to set up continuous interrupts for timer 1. So this is writing to that auxiliary control register on the user via, but FE6 6B. Now for our first timer, this first countdown, we're going to load the timer value with 5,000. But actually from that point onwards, once it's reached 0, we want it to count at 100 Hertz. And so this is 10,000 microseconds. And so as per that point before, we said, right, the latch takes 2 microseconds to load the counter. And so therefore we have to subtract 2 from this value when we load it into the latch registers. And I've got a quick demo of what that looks like here. So, no, actually, I didn't actually show you what the IQ handler is doing. So let's look at that first. Okay, so coming into the IQ handler, this time we're actually reading the interrupt flag register on the user buyer, all right? And the first thing we're going to do is check whether this flag is set, the bit is set for the timer 1 interrupt, and if not, we're just going to return to the OS as before. So in order to handle this timer interrupt, the first thing we're going to do is just load that value, and as we saw before, loading the timer low byte value just clears this flag for us. We're going to increment our counter, which is in 0 page. And then to try and see the effect of this happening, here all I'm doing is just taking the bottom bit from this timer counter. So this should go up 100 times a second. We're just taking that bottom bit, and then we're just twiddling the bits and writing those into the EULA palette register. Again, I think doing a masterclass on how the EULA works would be a great topic for the future. But for now, all we need to know is that if this bit is 0, then we'll get black. And if this bit is 1, then we'll get red. And so we should be able to see this effect when we run the program. So because the EULA has no effect in mode 7, at least the palette doesn't, we can run that from mode 2. And here we go. Right? We can see that it's now switching between black and red, and this will happen at 100 Hertz. So it's happening twice a frame. And it's roughly steady. Okay, it's not exactly steady, and that's because we're letting the MOS also service interrupts at the same time. So depending on what the MOS is doing, right, it's taking a slice of that time, and we are getting the interrupts occurring at different points. And so you will get this jitter, and it's sort of one of those constant things. The more you play with interrupts, like how do you reduce the jitter on interrupts, and how do you eventually, if you want to, I suppose the ultimate is get into a stable raster to reduce and remove this jitter entirely. But you'll be familiar from this so when you can see the dividing points on the elite screen, where you can sometimes see the division between modes 4 and 5 just flickers a little bit. But one thing to note here is that we don't actually know when our timer is actually going to start. Right? Of course, that went in the same place, but if I do this a few times, because we're just starting the timer when we run the program, it's just counting those ticks, and it's just starting from when I executed it. And so we can't actually place the position of the interrupt on the screen, but we can at least know that it's going to be regular, and it will happen at the frequency that we want it to.
And you've turned interlace off there.
Yes, that is a good point. Yeah, and actually I've covered the interlace example a little bit more detail in the last one. I can actually quickly demonstrate what happens if you remove that adjustment for 2. So if we make you can see ever so slightly, this is now starting to creep down the screen, and it's because we've got actually 2 extra cycles, 2 extra microseconds that we didn't want that it's taking to load that value. So you'll find that your interrupts just start ever so slightly going out of sync. Okay, so I guess the next step. So now we know that we can hook into the Vsync interrupt, and we know when the Vsync happens, and we also know we can set up a timer. The next step is to tie these 2 things together. So This would allow us to do things like delete changing mode partway down the screen or setting the color palette at a very specific point on the screen. And then this is also an entry point to some of the things that Rob mentioned earlier. So how we do more advanced graphical effects like vertical rupture. This relies on us setting CRTC registers at specific points on the screen before certain things happen within the video chip. And so we just need to now just set one of those timers to count down, and we can do that in the Vsync Interrupt handler. But it's actually important for us to know a little bit more about Vsync and when that actually occurs. If we want our timing to be accurate, we need to understand what Vsync is and when that happens.
Can I ask a quick question?
Of course.
What happens if your interrupt handler takes longer to run than the time between interrupts?
So they will, so either they can be re-entered, depending on exactly what the interrupt flag is on the CPU. So you can have another interrupt and it'll all come back in again, and that will happen in certain circumstances. If not, they just stack up, right? So your flags get stacked up, and the interrupt handler will be called again straight away, and you'll never sort of return to the system as it were. So they will kind of back up and get serviced one after the other.
Right. Thanks.
So I think, as I said before, we've got room for a much deeper dive on how the CRTC works and how the video signal is set up on the Beeb. But for our purposes here, it's enough to just know that in a typical setup, there are 39 character rows in a video frame, and usually only 32 of those are visible. And the Vsync position is usually defined at either row 34 or 35, depending on your sort of Star TV settings. And you can see this is outside of the visible portion of the screen. So we display 32 lines, the display gets turned off, and then either 2 or 3 rows later, the Vsync occurs, and this is the signal to the TV to sort of restart, go back to the top and start a new frame. But another important point here is that it's important to know that the Vsync interrupt itself actually occurs 2 scan lines after the pulse is sent. So although the Vsync position might be at, say, row 35, you won't get the interrupt until 2 scan lines later. And that's important because we need to account for that. In terms of timing, you can do the maths if you want to, but I'll just tell you 1 scan line is 64 microseconds. And we know again that by default, there are 8 scan lines per character row. So if we want to define an interrupt that will happen at a very specific scan line, and we're going to set our timer inside the Vsync interrupt, then we need to set up this value to be some sort of delay to the end of the frame. We need to adjust for that Vsync pulse delay, and then we need to add another delay in order to get us to the scan line that we want. So as a more specific example, say we want to delay from Vsync, which occurs at position 35, and we want to wait from there until scan line 128. Well, we need to wait 4 character rows, each of which is 8 scan lines. We need to adjust for the 2 scan line delay, and then we need to add our 128 scan lines. That's a total of 158 scan lines, each of which is 64 microseconds. And therefore, the value that we put into our timer is 10,112. So I've got an example of that. I'll walk through the code and then we'll take a look and see if there's any questions from there. So this is getting a little bit more complicated, but not too much, hopefully. So I'm just defining our value here to be, say, the total rows, which we said is 39, our Vsync position, adjusting for the Vsync pulse delay, and then here we've got our scan line we want to interrupt at, and this whole lot is multiplied by our microseconds per scan line. But I'll go into this a little bit more in a second. This time, just to mix it up a bit, I'm going to use timer 2 on the system via. So the first thing we're going to do is, timer 2 on the user via. The first thing we're going to do is enable Vsync Interrupt, which is on the system via. probably is already enabled, but I'm just going to put that in for completeness and just to show you how that works. And then we're going to enable timer to interrupt on the user via. So this is that bit there, and we're storing it to the user via enable register. Set up our IRQ handler as always, and then so we can adjust it afterwards, I'm going to store that timer value in 0 page, so we can fiddle with that and we can see what happens when we change that timer value. So the IRQ handler here is going to look a little bit more complicated, but hopefully you can follow this. First thing we'll do is check whether this is the Vsync interrupt, so this is the same as before. And if it is, we're going to use that same palette trick. We're going to set the background color to black. And so we'll know that will always happen at the end of the frame, and just reset that, that background. And then we're going to set up timer 2 to be the value that's from 0 page. So this is a one-shot timer, so we have to set it every single time we come into the interrupt handler here. So we just write those values into the timer 2 low order latch and the timer 2 high order counter, and then that second store there will make sure that the timer gets started. If it's not the Vsync interrupt, then we're going to see if it is the timer 2 interrupt. So again, this is checking this interrupt flag register, but on the user via. Check whether it's the bit that corresponds to timer 2, and if it is, we're going to come in here, going to clear the that flag, and we're going to set the background to blue. That's all we're going to do, and then we're going to return back to the operating system. So let's take a little look at that in action. So this time, this should always happen. This change in background color should always happen at scanline 128. But to actually check that, I've got a little basic program, very simple one. So we can see our rows here. And so this does now occur just on the boundary between rows 15 and 16. So this should be scanline 128. Again, you can just see the flicker here because there are other interrupts happening within the system, and the timer is being used for other purposes. I've set this up just to remove or add 64 from that timer value on the keys, so we can move this up and down, right? For each press, I'm just removing, subtracting 64 from that value, and you can see the effect it has on where this timer will fire. We can move it back down again. And in fact, if you look closely, you can actually see the that raster there just wobble a bit when I press a key, because of course pressing the key is an interrupt, and that interrupt will be handled by the MOS and handled in the MOS IRQ routine. So you can see that the effect that actually has on my IRQ, my interrupt handler when I receive it. You can see a little flicker every so often there. Not entirely sure what that is. Again, that's probably going to be some sort of collision of interrupts. The more you would want to do this, the more sort of control you would want to take over the entire system, which would give you more precise handling over when the interrupts occur, and reduce the amount of flicker. So that is that example. So you can see there how we tie the two approaches together, so using a timer interrupt and using the Vsync interrupt. Are there any questions at this point? Anything that's coming out of that?
Yeah, sure. How would you work around that small jitter? This might be a question for outside of this talk, perhaps. But I have seen that it's possible. How does that work?
So if you want, if you want just this jitter here?
Yeah.
Yeah, so there are different ways to do that. Most principally, if you want to achieve a stable raster, then normally, I can show an example another time, but normally you would involve reading the value of the timer when the interrupt occurs, and using that to compensate using a NOP slide. And so it means you use the timer value to jump into some code, and the length of that code depends on the value of the timer. And so you can compensate for this timer value, and you always end up with a sort of consistent number of cycles. And you use the this bottom few bits of the timer value in order to sort of figure out how many sort of NOP instructions you need to execute in order to compensate for the jitter that's coming.
Thank you very much.
It turns out to not be a huge amount of code, but it's one of those things that took us quite a while to figure out how to do that and how to make it reliable.
Yeah.
And it depends, because I mean, most of the time, most things you would want to do, I think you normally get, if you're running a machine code program, I mean, this is obviously running BASIC at the same time in the OS. If you're running your own interrupts and you're running your own game, you'll maybe get 10, 12 cycles of jitter. You know, that's probably okay for most purposes. You can time that interrupt so that it occurs in the horizontal blank, which I haven't really talked about, but you can make it so that that jitter occurs sort of off the side of the screen, for instance, so that for all intents and purposes, it appears to be stable. I think there's very few instances where you would need it to be, you know, truly stable. You can normally hide it. And it's why a lot of games just had a couple of blank scan lines in between sort of different parts of the screen. And for effects like vertical rupture, you don't actually have to be that precise most of the time. You just need to make sure that you're changing your CRTC registers before you reach a particular point. So say we were rupturing the screen in this bottom part, we would need to change the registers before we got to here, say. And so you've got usually a reasonably large target to aim for.
Oh, thank you.
Cool. Right, I will carry on. Last example. This is, I suppose, just a more advanced version of the previous one. So one of the questions that seems to come up a lot is like, how do we reduce or avoid flicker of sprites? And this is just one way that you might try and do this. Obviously, numerous ways to try and reduce and avoid sprite flicker, but one way we could do this is by using a timer. And so I suppose it's worth probably just quickly discussing or just mentioning why sprites do flicker. If you're not double buffered, if you're only using a single buffered screen, then if you modify the screen memory at the same time that those bytes are being sent to the display, then things are going to happen. And this is because the video chip generates these screen addresses quite a fast pace, right? You're going through at 2 megahertz. You're sending 80 bytes per scan line potentially to the screen in a high resolution mode. Then if you change that RAM address at the same time as that, then you're going to get some sort of flickering or tearing. If you, in the middle of doing an erase, then you're just going to send blank pixels to the screen. And then by the time you've written them, then you're already too late, right? The raster has passed and those pixels are never going to get sent to the display. And so one way of doing this is to use a timer so that we call our sprite routine after the raster has passed the bottom of our sprite. And that way, in theory, as long as we complete our sprite routine before we get to the top of the sprite, then it can't possibly flicker. That's the theory. And so here is a sort of specific example. If we want to plot our sprite at, say, scanline 100, and it's 16 pixels high, then as long as we call our routine after scanline 116, and as long as it completes before the raster comes back around to scanline 100 at the top, then it shouldn't flicker. That is at least the theory. So I've got an example of that here, our sprite example. And in this one, we're going to actually set the timer dynamically in the Vsync handler based on the vertical position of the sprite. So for this, I am actually turning off the interlace here, tricky as you mentioned, so that we don't get any drift. For this one, I'm using timer 2 on the system buyer, and it's going to be a one-shot timer. So we're enabling the Vsync and timer 2 interrupts, and then setting this control register so that it's a one-shot. And then I've removed all the sort of spritey bits. They're in a separate file, so we don't need to worry about those. But essentially our main loop here, I'm going to check for some debug keys so I can show you what's going on. I've got a little routine that just moves the sprites, but all I'm doing is just literally setting the Y value. And here I'm going to use a flag. So basically we're going to sit in a loop here, just waiting for this flag that's telling us it's safe to plot. So when this 0 page value becomes non-zero, we're going to go, right, that's the signal that we should do our sprite plot. And so we can see what's going on. I'm using another one of these cunning raster tricks. So we're going to set the background color to green so we can see when this loop actually happens. We're going to erase the old sprites and literally just wiping the memory. I'm not doing any fancy EOR or anything like that. I'm going to set the background color here to blue, and this will allow us to time how long this takes, right? How long does this deleting of the sprite take? We should know this because we'll see the background color is green. And then we're going to plot the new sprite, and we'll be able to see how long that takes because the background color is going to be blue. And then when we've finished everything, we're just going to set the background back to black and jump around to the top of our loop again. So that's just going to be our simple little loop just for a moving sprite, and then we can have a look at how that interacts with the raster and how we can use the timer to help. And so this bit's a little bit more complicated, but again, hopefully should be okay to follow. I'm actually going to have two code paths. I'm going to show you a fixed timer where if we come in, and this is the Vsync handler here. If we're using a fixed timer, we're just going to set the flag. So this might be analogous to normally we would just wait for the Vsync, either with like a StarFX19 in BASIC or waiting for the Vsync handler normally, and we're just going to plot the sprite as soon as the Vsync happens. That's quite often a common way that people would set up their routines and set up their main loops. It's just drawing as soon as Vsync happens. Or we're going to set up this dynamic timer, and our timer value is going to be the same as we had before, so this delay to the end of the frame. We need to obviously adjust for our Vsync. But then the scan line we're going to choose to interrupt at, we're going to actually calculate that from our sprite position and the sprite height, because we want to signal to start the drawing at the bottom of the sprite. Thankfully, this top bit is fixed. So we've got a constant here, this kind of base value. All we need to do is calculate this additional part to add, which is obviously our Y, plus the sprite height, and we need to times that by 64. Because, of course, this is a 16-bit value, we need to do a 16-bit multiply here. Obviously, this is not the most efficient way necessarily to do all of this, but hopefully should be relatively clear. So for the low bytes, we're just adding the height to Y, and then we are rolling this 6 times in order to multiply this addition by 64. And then we can do a 16-bit addition here to add to the base value, and then set our timer to low order latch and our timer to high order latch. So hopefully that makes sense. We're calculating, as I say, this timer value dynamically as sprite Y position plus sprite height times 64 plus this sort of base value that we've got to get us our final position on the screen that we want to wait for. And then if we're using this interrupt, this is our timer 2 interrupt handler. Again, we're just going to clear the flag, the timer interrupt flag. We're going to set our flag here to say, yes, now is the time to do our sprite plotting. So let's just take a little look at what effect that has. So this is what happens if we try and plot our very large, so this is 64 by 64 sprite in mode 1, and this is calling the sprite routine at Vsync. So this is using the fixed timer. If I turn on the debug display, you can see why that's happening. So this green part, as we said before, is where the sprite's being deleted. It's just literally writing zeros to the screen. And then this blue part, because it's a large sprite and it's not a desperately optimized sprite routine, you can see this is how long it's taking to draw the sprite. And so we get this rather hideous flicker. And it actually, you can see it makes you can see why this is happening if I actually just single step a frame at a time in JSBeeb. So you can watch it start to disappear with each frame. So obviously here, because we're only sort of about 40% of the way through the blue part, it's only had chance to draw 40% of the sprites, but we've already met where the sprite is on the screen in the raster, so you just don't see the rest, right, because it's been deleted. You can see that gets worse as you get to the top of the screen. And as we keep stepping, you can sort of see it reappear. Like that. So that's sort of a really extreme example that I wanted to show you, like how bad that can get. But if we use a dynamic timer, we can actually remove that flicker entirely. And that's because if I turn on the debug, you should be able to see this a little bit more. We're actually moving the point on the screen at which we are setting that flag and therefore triggering the sprite plot routine to take place. And again, if we just single step this, you can see this green part here is where we are doing the arrays. And then when that's finished, we've got the blue part, which is doing the sprite plot. We're moving that on each frame so that it's always going to be at the bottom of where our sprite is. And as long as this completes before we get to the top of the sprite, say it's quite a long loop, right? We're erasing quite a chunk of the screen, and we're also trying to draw quite a chunk as well, all in mode 1. But you can see it won't ever flicker because it never actually meets the raster. And that is the end of where I am at. Quite a lot of material to go through there. It's quite dense, but hopefully there are sort of 4 reasonably useful examples of in different combinations of like how you use these different parts of these chips in order to set timers or use the Vsync Interrupt. So I'll post a link afterwards. I mean, it's all on GitHub now. The code's there, and this just this little bit of text as well. And yeah, hopefully after sort of having a look through that and having a look at some of the examples, like then going into the advanced user guide, you know, it starts to make a little bit more sense. It certainly took me a good few times sort of trying these different things out before it made complete sense. But so there's quite a lot of subtlety as well in terms of what happens when you set certain registers and certain flags and things like that. So again, it's kind of worth having a read through, particularly this sort of table here about what happens when you write or read these different timer registers. Like different things happen depending on which register you read and or whether you're writing to them.
The thing about interlace was that without interlace, it's exactly 39 character rows. With interlace, it's 39 rows and half a line, time-wise. Is that right, Kieran?
Oh, you know better than me. Yes, I think so. It's half a scan line, isn't it? Yes.
I think so.
In general, turn off interlace. It makes life so much easier.
Unless you want to do high-res mode 0.
Well, yeah.
Oh, that's great. Thanks. The latches, when you was talking about latches, it suddenly went click. That makes sense.
Yeah, the latch is definitely, definitely one of those things that takes a bit of a while to get your head around. The fact that it sort of has 2 copies of these things, and it uses one set in one case and one set in another case.
And I'd completely forgotten about reading one of the timers clears the interrupt flag.
Yes.
I mean, you may not want to use that feature, but sooner or later it will save you days of debugging.
Again, there's sort of quite a lot of subtleties there, which is, again, I couldn't possibly cover every edge case, but yeah, hopefully there's some good examples there, and just some of these maths that have taken a while to get right in terms of knowing about the Vsync interrupt coming after the pulse and knowing about the latch load delay. These are sort of quite important, subtle things that can just cause a lot of pain. When you, why doesn't it work, or why is it drifting, or why is it not moving? Why is it not working?
I think there are also differences between timer 1 and timer 2.
Yeah, timer 1 runs continuous. Timer 2 has a pulse
Yeah,
mode.
some different modes, I think. Yeah.
Yeah. I'm sure somebody can tell me what that's used for. I don't know.
I think it's to use with the shift register,
Yeah.
but not used either.
I need to ask Chris. I'm sure Chris has used the shift register.
Yeah.
It must be for driving some sort of peripheral. Which, well, thank you everyone, and yeah, great to hear your feedback on sort of whether having code examples is more useful to actually look through. Obviously, they take a bit of time to prepare, but it's actually quite fun. There's not a lot of code here, or whether actually sort of trying to consume assembler live is a little bit much. But I wanted to sort of do some concrete examples. So even if you come back and look at these later.
A quick question about the interrupt handlers, where it stores the value of is FC from?
Yeah.
Is that just where the OS has stored a copy of the A register outside your? So yeah, that's where you restore it at the end for the previous handler. Okay.
You'll often see this omitted from IRQ handlers. All you'll see is at the end, you'll just see load FC and then return, which is okay if you are not wishing to interact with MOS, and also if you're sure that you're never going to re-enter your IRQ. But if there is any chance that you are going to re-enter the IRQ, then you should do this.
Okay. I've seen some other examples where they're also pushing X and Y as well. Is that needed at all?
If you use them, yes. All of these examples only use the accumulator. If
right,
you
okay.
touch a register, you must restore it.
Okay.